So the next speaker of today is Jacquet. He is from the Université Paris-Sorbonne, I think. Hopefully I didn't butcher that too much, pronunciation. And he's going to talk today about quantum vacuum excitation of a quasi-normal mode in an analog model of black hole spacetime. So Maxime, please, the floor is all yours. You can start.
Thank you very much. Thank you very much for the introduction and for having me today. It's really nice to talk at RQI, and I really hope that next time we will all meet in person. That would be even much nicer. Okay, so today I want to tell you about a bit of theory that we've done in preparing an experiment that we are running at Laboratoire Kessler-Brossel in Paris. And this theory that we did sort of like revealed some surprises in things that we can see in the lab and in what analog models of gravity are able to do. And specifically, we are going to see that with analog models of gravity, we observe a new effect, which was not really expected, I guess, or not in the form in which we are seeing it. Okay, so the talk I want to give is something related to analog gravity and considering a Schwarzschild black hole with a vacuum or a quantum field in its vacuum state on the Schwarzschild black hole. And what I'm considering is really the sort of like second period of the Schwarzschild black hole when the black hole is isolated from everything, basically, and just living there in its curved space-time. So I'm not considering the formation time. What we know about the black holes in general is that if they are perturbed, and say perturbed very strongly by a very strong or large amplitude F object, then they will release gravitational waves. And we have seen those gravitational waves, so we have trust in this theory. And gravitational waves are quasi-normal modes of the gravitational field. But in fact, there are other fields on the space-time. So for example, scalar fields, massless scalar fields, and these also have quasi-normal modes. And they will also get excited upon perturbation. And the talk today is about the fact that these perturbations can come from the vacuum itself. Very famously, the scattering of vacuum fluctuations at the horizon or near the horizon of a Schwarzschild black hole yields Hawking radiation. And this is what we wanted to observe in the lab. And that's the type of calculations that we are going to see today. All right, so of course, we try to do that in the lab. So we resort to Unruh's famous analogy of a transonic fluid flow with the curvature of space-time. And transonic fluid flow creates an analog event horizon or acoustic horizon at the point at which the flow velocity of the fluid equals the speed of sound. And this is all very formal. And in the paper that I highlight here at the bottom of the screen, I show how to do this with my specific fluid. Very famously as well, Hawking in 1981 showed that at the acoustic horizon, the quantized acoustic field will give us Hawking radiation in the form of Hawking radiation and its partner wave, which will be correlated. So correlations, in fact, are the things that I want to observe in my experiment. So with my specific fluid, which is called microcavity polaritons, and I'm going to tell you everything about microcavity polaritons in 1 second, the very simple picture drawn initially by Unruh looks a bit more complicated, so it's on the left. And in the paper that I highlight at the bottom that was just published, we show why we need such a complicated flow profile in order to get Hawking radiation that would be observable in the laboratory. I'm going to show some numbers later on. But so basically what we have is that we have a fluid that flows with the orange velocity that's initially subsonic. And we see that because its velocity is initially lower than that of the speed of sound, which is in blue. And at some point they cross. There is a sonic horizon there. And we have managed to have a very steep horizon, which usually gives a relatively steep Hawking radiation. Okay, so we do this with microcavity polaritons. Microcavity polaritons, you can think of them just as a quantum fluid, and you can like just bear that in mind for now, and you can ignore the next 3 slides if you wish, or you can understand what they are, and now you follow me. So basically, microcavity polaritons are quasi-particles that live inside microcavities. So picture yourself 2 mirrors that are facing each other. Laser light is coupled in between the 2 mirrors by the back of one of those mirrors, and it bounces back and forth in between the mirrors until it eventually exits. So all the dynamics are happening in the plane of the microcavity in between the 2 mirrors. In between those two mirrors, there is another semiconductor that is placed, namely a quantum well, in which the laser photons will excite excitons. So these are electron-hole pairs. And in certain conditions, so we need to have a very cold sample around 4 kelvins, the photons of the laser will also strong couple with the excitons, and this will form two new eigenstates of the system. So if we look at the picture on the right, which shows the dispersion inside the cavity, we have the frequency running upwards as a function of k, the wave number, and this is all symmetric around by rotation. We have cavity photons that have a massive dispersion in blue, and we have quantum well excitons which also have a massive dispersion, but they are so massive that here they appear to be flat. And when they couple, this creates the two new eigenstates, the lower polariton in green and the upper polariton in green as well. And for thermodynamic reasons, we are only going to work with the lower polaritons. The dynamics of these lower polaritons in the plane of the cavity is described by a Gross-Pitevsky equation. It's a kind of nonlinear Schrödinger equation, which here also accounts for the fact that we have some losses. As I said earlier, eventually the photons exit the cavity, so they carry with them the properties of the excitons, or the polaritons, I should say. And we pump with P continuously. So this system is interestingly out of thermal equilibrium, and this is very interesting for two reasons. First, there is an experimental reason, which is that we just can look at the light that comes out of the cavity, and by looking at this light, we know everything about the polariton field that lived inside of the cavity. It's much simpler than, say, an experiment with atomic Bose-Einstein condensates or liquid helium or whatnot. Here, we look at light with a cheap camera, and we see live what's going on inside of the cavity. And the second reason is that we have out of equilibrium physics for free, which is also very, very interesting, as we will see later. So I can send my laser light here on the dispersion diagram. We see it, it's this red dot. So it's a frequency that is very close to the lower polariton range. We call it resonant. And if I drive my polariton field with a resonant laser field, the density and the phase of my laser field become the density and the velocity of my polariton field. And the photons that come out of the cavity give me, via their intensity, the density of the polariton field, and via their phase, the velocity of the polariton field. So it's really an all-optical experiment. I can do everything optically. I just need to cool down my sample and shine a laser upon it. And my sample here looks like what's on the top of the screen. It's basically a very elongated wire that's very thin, so the dynamics are really one-dimensional now. And at some point, I etch a little bit along the wire to create a negative potential. And I am going to pump in that wire to create a density of polaritons. So the density of polaritons which I create with my pump, which looks like a step-like profile, looks like the blue profile on the right-hand side. So by the square root of the density, we recover the speed of sound, and numerically we can see that we obtain this complicated flow velocity profile, which is again forming an event horizon. There is dispersion on either side of the interface, on either side of the horizon. On the left-hand side, it's subsonic. On the right-hand side, it's supersonic. The dispersion looks very much like those of atomic Bose-Einstein condensate. In blue, we have the positive norm modes, and in red, we have the negative norm modes. So because we have some negative norm modes that oscillate at positive frequencies in the upstream region, in the supersonic region, sorry, we will have a mixing of annihilation and creation operators. So we will have the Hawking effect. So this is the setup. And now I've got 3 minutes to explain to you what's new about it. So basically, I have a horizon, the horizon of a Schwarzschild black hole. And as I said earlier, if the Schwarzschild black hole is perturbed, we know that it releases gravitational waves. So what I'm going to do is that I'm going to perturb my black hole, or my horizon. I'm going to send in a wave packet from the left that's going towards the right. And we see here on the space-time diagram on the right, the wave packet impinges, or the front of the wave packet impinges on the horizon at x equals 0, at t equals 0. And it's partially reflected and partially transmitted. That's the Hawking effect. But there is something more that happens. If we look carefully at the picture, we see that at x equals 0, long after the wave packet has left, the density is still oscillating. Okay, so there seems to be some metastable state here. If I look at this metastable state, I just plot here the evolution of the density with time. So it's a cut along the vertical axis of my previous figure. I see that I have the density that decreases, and that can be fitted with an exponential or with a complex frequency with an exponential decay. So,
Maxime, 2 minutes.
Yeah. Yep. So I got here the coupling between a mode that's or between the density that's localized near the horizon and modes that propagate in and outwards to de-excite the horizon. So I've got a quasi-normal mode. This was with a very large wave packet, but in fact, I can also do it with a very small wave packet, namely the quantum vacuum. And I will finish on this basically. Here I have a simulation, a truncated linear approximation, where I just have the quantum vacuum that's impinging on the horizon. And I get the Hawking effect, that's this very long mustache here. And I also get localized oscillations. So basically, we see that we have correlations with x prime equals 0 and the entirety of the space-time. And this again is my quasi-normal mode. We find the same frequencies, and this can basically be, oops, something happened. This can basically be explained by this peak that I have in the flow velocity. As I said earlier, this peak is essential to get a very steep horizon, but in fact, it also creates a sort of like local negative potential for modes near the horizon. And these modes create a standing wave and of negative norm that basically de-excites the density of the black hole near the horizon. So I have here with my polaritons a mechanism for vacuum fluctuations to come and excite, well, Hawking radiation, of course, but also quasi-normal modes. And this shows up in the spectrum. In fact, we can see that the spectrum, instead of being semi-Planckian, has a peak, which is very surprising. And it's quite interesting because it means that in our experiment, we will be able to see spectral modulation of Hawking radiation by quasi-normal modes that come from vacuum excitations. And this raises many questions which I have no idea about, but you guys are experts on it, so I leave them out here for you. But basically, this seems to be a very generic effect. In the paper, we show that this is a very generic effect. So I would like to know whether it's possible to sort of like do some similar calculation with the actual Schwarzschild black hole, and whether this gray body factor tells us something. And now I leave you with my concluding slide and all the papers that are related to this talk, and also an exciting prospect, which is that we have some experimental data, which shows a very nice flow profile with a very nice peak. So we should be able to see this effect in the lab very shortly.
Thank you, Maxime. So now maybe we have time for a very short question. Albert, please go ahead.
Yes, so there was a lot of interesting things here, but maybe there was a very basic thing that perhaps I missed. I would have expected that before you introduce a non-trivial flow, background flow of velocity and so on, your light, that that the spectrum of your quasi-particle, the dispersion relation of your quasi-particles at low k would be linear. If you but that is
yes.
not from your
yes, okay. So in fact, here I am showing a relatively large range of k just to show the full dispersion. But in the say in the upstream, in the downstream region where the flow is supersonic, in fact, we see if we would zoom, we would see that the dispersion is quite linear. In the upstream region, this is not the case, and this is because of out of equilibrium effects in the polariton fluid.
But for example, I guess was in earlier slides, the first slide when you introduced the dispersion relation, your two sort of polariton. Yeah. So that was presumably for a constant background, right?
Yes, exactly. That's for a constant background.
And there you don't have for low k a linear dispersion relation.
Okay, I guess this picture is not exactly right that I am showing here, but the region where the dispersion would be very linear in the polariton fluid is rather short. So it's like sort of like 0.3, 0.4 k, or in k in this scale it's 0.3 to 0.4. And I should
Okay.
perhaps correct this picture.
Because I guess I was expecting that this thing here should correspond for low k to massless particles in Minkowski, right?
Yes, so in fact,
That's what I-
in fact it does, but for very low k. Yeah.
I see. I see. Okay.
In fact, it also doesn't matter that we don't really have this linear dispersion. I mean, of course, it brings us further away from the analogy by Unruh, but the effect survives. We still get Hawking radiation. So it seems that the dispersion is not so important.
So you get off something that looks like massive particle, massive.
Yeah, if you want, yes, there are free particles. Mm.
Okay. Okay. Thanks.
Thanks for the question, Robert, and let's thank Maxime again.
Thank you for having me.